Right. So what I'd like to do for you guys is to summarize all the conventions and the different nomenclatures we've used for lenses, right? And kind of show you guys how I think about this because I can never really remember all these things. So the one thing that I remember is that this is a positive lens. This biconvex kind of Sherlock's Holmes magnifying glass lens is what I consider the positive lens. Is the one thing that I remember, and this has a positive focal length, right? And we can look at the lens equation, which is 1 over f is equal to n minus 1, 1 over r1 minus 1 over r2, and we can figure out how we can have it so that this equation always gives this lens a positive focal length. These types of lenses are all positive. Another thing to notice about this positive lens is thicker in the middle and thinner at the edges. That's another defining characteristic of a positive lens. And if you just remember this is a positive lens, then you can kind of pull that out from there. But how do I make sure that this number here always ends up positive? Well, this number, index of refraction, is larger than 1 for most materials, almost all materials. So this is a positive number, right? And then here, I'm going to take a number minus another number, right? If this number is positive, and I subtract off a negative number, right, minus a negative number, that becomes a positive, and I have a positive plus another number, and that's always going to be positive, right? So for this type of lens to always be positive, this is a plus f, then it makes sense that R1 would need to be positive and R2 would need to be negative. Right? We can then take this and extrapolate this as noticing, well, that means that the lens shape that I have as being positive is part of a bigger circle where the center is to the right of this axis of the lens surface. Right? So that tells us that for a lens, when the center of curvature is to the right of the surface, that surface is given a positive sign, positive radius of curvature. On the other hand, for the other surface, R2, that has a radius of curvature, center of curvature that's over here on the left of the surface, and that we decided has to be a negative radius of curvature. So this is a negative radius of curvature here. And we'll do the same kind of color coding we had with on slide. But then that lets me extrapolate beyond that to other shape lenses. If I then take this and say, well, what happens if I have a lens of this shape? Okay, well, if I have a lens of this shape, and this is my R1, and this is my R2, this now has a radius of curvature for the first surface that I encounter, assuming the light's coming from the left, that is to the left, right? And we agreed earlier that if it's to the left, look at the pink surface here, and its center of curvature is to the left, that just from working out the logic from that guy, that was a negative surface. So this is a negative surface. This one has a surface as part of a circle. I hope you guys can see this. I'm not going off the screen too much. Let me rotate that just a little bit. That is to where the center of curvature of this one is clearly to the right of the surface. And over here, when the center of curvature for the blue was to the right of the surface, we labeled that with a plus. Right. And let's double check that our equation will guarantee this is a negative lens. 1 over f is equal to n minus 1 times 1 over r1 minus 1 over r2. This is positive, but then this is a negative number because of that, and we're going to subtract a positive number. And an already negative number, subtracting another number will make it more negative. Take that negative times that positive, and you get a negative focal length. Notice that for a negative lens, it's the opposite. It's thinner in the middle than it is at the edges, right? Keeping those ideas in mind, we can now evaluate other lens surfaces. Right? If I have something that's a crescent type of lens, like this, right? Now we can ask, how do I deal with this? Well, I have an R1 over here, assuming the light's coming this way, and an R2. Let's say we're given two numbers, right? Let's say we're given that the two radii are 10 centimeters and 20 centimeters, but we aren't told which is which, right? Absolute value is 10 and 20, right? First of all, let's figure out whether they're positive or negative. Again, we look at this and we say this thing has a radius of curvature that's part of a bigger circle that's over here, right? So for this, let me color code it. Let's make this one orange, right? So for this first surface, it's part of a circle where the center of curvature is to the right. If it's to the right, we said, looking at any of these other cases, that gives it a positive radius of curvature. This one, I'll label in green. Right? This one, R2, is also part of a bigger circle. It's actually a much bigger circle, and that has a center of curvature out here somewhere that's also to its right, so that one's also positive. Right? Now, if I had to ask you whether this is a positive lens or negative lens, you can take the logic we've already developed and say, well, it looks thicker in the middle and thinner at the edges. That reminds me more of this lens, which we know, that's our classic lens, that's a positive lens. So if I had to guess, I would say F is positive for this, right? Let's see how we get that. Well, we have two radii of curvature, and I really think you should draw these circles out, because we have a tendency, if you looked at just the lens shape, there's a common mistake, and that is to say, which of these has a larger radius of curvature? And I think what a lot of students are doing is they're accidentally, this is wrong, picking this one to have the largest radius of curvature because it's a longer curve, right? There's more length here, right? And this one looks like it's shorter, and so you might say, oh, that's part of a smaller circle, but you can see if you draw it out that the one that has more arc to it is actually more curved, which makes it part of a smaller circle. Whereas things that are more flat, yes, it has less of an arc here, right? This arc length is shorter than this one, but that's because it's part of a big, big circle like the Earth, right? So it turns out that R2 is actually the bigger one. So this would be the one that's, say, 20 centimeters, and this one would be the one that is only 10 centimeters. So then if we look back at our equation, and I'll write it up one more time, I think I can go as far as over here, and we have 1 over F is equal to 1 over, n minus 1 times 1 over R1 minus 1 over R2. Right, let's see how this gives us a positive number. R1, so it's n minus 1 times 1 over R1, we decided is a smaller radius of curvature. So that's a small, 1 over a smaller number, minus 1 over a bigger number, because R2 is the bigger radius of curvature. And that gives me n minus 1, which we already know is a positive number, times something that is 1 over a small number is a bigger number. Call it bigger. And 1 over a bigger number is a smaller number. Right? And they're both positive, because we both said they're both positive radius of curvatures. So a big positive number minus a small positive number still gives you a positive number. Positive minus positive, That gives this whole thing a positive times a positive, and we get a positive focal length. Does it make sense as a positive focal length? It's thicker in the middle and thinner at the edges, so yes, it makes sense as a positive focal length. You can then do the same thing for a different lens shape. Like we came back here, and we do the last lens shape, which would be a lens that is got a real sharp arc on this side, and then a smooth arc, or shallow arc on this side. Like this. If you had to guess whether this is a positive or negative lens, the first thing you would do is you say, oh, I remember for my stereotypical lens, this is positive, and this is wider in the middle, thicker in the middle, and thinner at the edges. So that's my positive. So this one, which is thinner in the middle and thicker at the edges, my best guess would be that this is a negative lens, right? And then you could work it out. Now, which one of these has a larger radius of curvature? Again, I emphasize drawing it out and realizing that this is part of a big circle, whereas this one is part of a smaller circle. And then you could look to see, are these positive or negative, right? The way I've drawn it, this one would be, again, positive because it looks like this. It's bowing out to the left. This one's also positive, right? But now because the bigger number is actually on the left, that's where you'll flip it around and get a negative sign, this one being a negative lens. If we flip this over, right, then the first surface no longer is the bigger number, it becomes this one, right? Once we flip this thing over, if I flipped it over to make it look like this, a lens that looked like this, that lens, which is kind of, I'm trying to flip over that one, let me make this a little bit more extreme. Right? This is still a negative lens because it's still thinner in the middle and thicker at the edges, but now this one, which we said is a smaller radius curvature, is the first one, and this one is the second one. But, and that seems to be flipping stuff over, and you say, okay, well, don't I get the opposite result? Well, no, because now if you look at each individual surface, this one looks like this one, and we decided earlier that this was a negative. So now because we flipped it over and it's bowing to the right, the center of curvature is to the left, and that's a negative surface, and this is a negative surface, but the big and small number are flipped over, everything will cancel out, and this will have the same focal length as this, and they're both negative lenses. Right. Then, if you have to do mirrors, you just have to kind of remember the idea that mirrors are kind of the reverse of lenses. Right? Lenses pass light through, mirrors reflect them back. And so whereas this shape for a lens was positive because it gave me, if I took sunlight in, it allowed me to focus and form a real burning point right there, a real image of the sun that I could then cook an ant with, right? If that's what I consider my normal and positive case, then how do I get that same situation with a mirror? Well, in order for sunlight coming in to actually come down to a focus with a mirror, I need it to be shaped like this so that it sends the light inwards to a point and can cook an ant right there. So this is what I consider positive for a mirror, right? And this has a positive focal length. So and you remember the focal length is 1/2 the, so actually I draw this a little bit weird. This would be at the focal point, and the center of curvature would be out here, right? That would be R. That's the radius of curvature from the center to the edge, right? If this is a positive focal length because it's a positive mirror, then this has to have a positive radius of curvature because the focal length is just 1/2 of the radius for a mirror. But that tells us that, oh, when this is now the opposite as it should be for a mirror that is a lens. In the lens, we said if that first surface was bowed to the left, bowed outward to the left, that's what we had as a positive first surface. Here, for a positive mirror, we go R is positive when it's bowed to the right, which is the exact opposite of for a lens. But that makes sense because we think of mirrors as doing kind of the opposite of lenses. Instead of passing light through, it reflects it back. And then you can do the same logic for DIs and DOs. Right? When you have a positive lens, one we work with all the time and we think of as our basic case. Right? If I have an object out here, far and away from the lens, I will create a real image over here. This is where real images form for my positive lens, right? So then, if this is the real image space for a lens, and this is then where, this is over here is where DI is positive, when it's over here, then when it's virtual, well, that's the reverse of a real image. So for my typical case, if real images are positive DIs over here, then virtual images for this typical lens will show up over there. Right? So I'll put this up here, real image, and DI is positive, and DI is negative for virtual images. If instead I were working with a mirror, we know mirrors are the reverse. So if I have my positive mirror, so I'm only going to switch one thing at a time. I'm going to keep it positive, right? And I'm going to make it a mirror instead. I only switch that one thing, keep it positive, but make it a mirror. Then if I have an object over here, these are going to ray trace so that I get a virtual image, a real image over here somewhere. It'll be inverted, as all real images are, and it'll be over in this space. This space is now my normal space, not the space behind here, right? Because behind was what I expected for, behind the lens is where I expected the real image to show up. But for the reverse case of a mirror, which reflects, then real images with DI positive is going to be on this side. And when I end up with a virtual image, it's going to be on the opposite side. That's going to be over here where DIs are going to be negative.